Okay, so chapter 6 is about implementing indexes, views, and full text search. Now, because these are long topics, I will have to split this into maybe 2 or more lessons. So today I'll focus on indexes, and maybe the next one we'll come and look at views, then we can look at full text search. The objectives for this chapter are to create and manage indexes. I'm using the term manage in a very broad sense to include changing or modifying indexes after they are created, enabling indexes, disabling indexes, as well as deleting indexes. In a similar way, we have the second objective, which is to create and manage views. Again, here we'll be looking at not only creating views, but how you can modify views which have been created or enhance the views which have been created, as well as to delete those views when they are no longer needed. And the third objective is to implement full text search. Okay. That's the overview. Now, starting with indexes. SQL Server allows you to create indexes on tables to enable quick access to data. The main purpose of indexes is to make your queries efficient, is to make your queries be able to retrieve data in the most efficient way, in the shortest possible time. You need to bear in mind that some databases are going to be quite big. Some databases will have tables with thousands or millions of rows in them. And when you are searching for data, searching one row at a time up to the end can be time consuming, even for the best of machines. So there are algorithms or approaches which have been devised which can greatly speed up the process of searching for data in such large tables. And one way to implement that is to create indexes on the tables. You also need to be able to look at how exactly the database management system is carrying out the queries. So to do that, you look at the execution plan. In the Management Studio, you can view how the results were obtained, the intermediate results which were obtained, and the final results which were obtained, and all the statistics to do with each of those tasks, how long it took to perform each of those stages, and so on. And you can have control over how the execution is carried out. Of course, this is not something that you have to do for each and every table, but there are certain instances where, as a database developer, you need to be able to control how the query is executed by the database software. And I'll be showing you how you can view and control or change the execution plan. Okay. Indexes are needed because most of the real life applications of databases will require that you have a lot of information. For example, if you are looking at a university like University of Zambia, there are probably 30,000 students. So some of the tables containing information might have maybe 20,000 rows in them. And unless you fine-tune your queries, it can take a while for the results to be retrieved, and it's going to show in the performance of the application that you are developing. And once your database is underperforming, that can lead to frustration on the people using it, and that can make you unpopular. And in some cases, that kind of application may not pass the acceptance test by the user. So when you're developing applications to make use of the database backend, you from time to time need to fine-tune the performance, particularly the execution of queries. And one way in which you can do that is to manage indexes properly. An index is a data structure which is associated with a given table. It enables data to be searched very quickly. It speeds up the process of querying data from a table. There are two main benefits of using indexes. The first one is it will accelerate the execution of queries, especially when you have queries that have to operate on multiple tables, such as those which will make use of joins and perform other tasks such as grouping results, sorting results in a given order. So to speed up that process, you can use indexes. Secondly, you can use indexes to enforce the uniqueness of rows in the table. We have already seen that when you use primary keys, they require that every value in that column should be unique. But that's not the only way that you can speed up the process. You can also use indexes to further enforce the need to have unique values for different rows in your table. So those are the two basic benefits of using indexes. Now, indexes contain two components. They have the keys and the pointers. Keys are values built or obtained from one or more columns in a table. That is, the values taken from the columns that where you have configured the index. Pointers are addresses to memory location where data pages are stored for different sections of the table. You can look at this, this illustration of the keys and pointers. When you have a table, you can have values with employee numbers of different values. Those are going to be used as keys. And then the database management system is going to create pointers for different sections of that table, which will correspond to different locations in the computer's memory where the data is stored. The idea is when looking for a certain employee number starting maybe from a given number, the database software is going to first look at which page to go to. It doesn't have to search everything in that table from the first up to the end. Okay, so it's going to have keys which are going to be values taken from the column on which the index has been defined, and there'll be pointers which are addresses to memory location where different sections of the table are stored. Now, I was saying the normal way of organizing things is to just put them in the order in which you receive them. For example, I have this table with the names of towns. I just enter the towns as I receive the information. This is okay for a small table. So if I need to check for a certain town like Choma, I just need to start from the beginning and check all the values or the rows in the table until I get to the value I'm looking for. I can go further because sometimes the same value can appear more than once, so I'll go up to the end of the table. Now, this is not an efficient way when you're dealing with large tables. Imagine you have a university with maybe 70,000 students, current students, and then you have also past students who may have been there maybe 10, 15, 20, 30, 100 years. So you can have thousands or millions of rows in a given table. And to search from the top to the bottom of the table will be tedious and will be slow even for the best machines. So for large tables, there are different approaches used to searching for values in the tables. Now, the approach that you take to search is called an algorithm. An algorithm is a set of steps that you can carry out to achieve a task. Normally, an algorithm is independent of the implementation. What I mean is that it can be applied to a wide range of applications, similar applications. And I was saying that this is a topic that I think you'll be might be covering with McBride. I don't know, I haven't looked at the syllabus, but for now, I just want to explain this. In SQL Server, apart from searching information in sequence from first to the end, there is also what is called a B tree structure. It's a data structure algorithm. B here stands for balance. Okay. Okay. Not binary. Okay. Now, this structure is something like this. You start from there and you can search for information because the information will be arranged in a hierarchy. Okay. Depending on which implementation you have, the B structure uses this formula where it says low plus I'll briefly show you how this can be done. Okay, so the starting point is going to be determined by a formula. So in this case, you can work out the formula depending on what is the first row and the last row in the table. And this information is stored in one of the system databases in SQL Server. In the B-tree data structure, data is indexed, is organized in a hierarchy in different levels, where at each level you set nodes. So these are nodes here. There's a node here. And this one is called a root node. Okay. It gives the picture of an invented tree. The roots on top, the branches and leaves which will be down there. So these will be the leaf nodes. These are intermediate nodes, which can just be one line, or they can be multiple levels for the intermediate, depending on how complex your data is. Okay. Now, for each table where you have set an index, there is going to be the starting node, which is called the root page or root node. at the top of the tree. And that is going to branch off into 2 or more branches. And these branches are also going to have their own nodes, intermediate nodes. And further, those intermediate nodes are also going to have their own branches until we get to the leaf level or the branch level of that tree, which will be at the bottom. And this will indicate the table in which data is stored in the database. Okay. Now, for SQL Server, there are 2 types of indexes that are commonly used. There are others, but they are less common. These are the clustered index and the non-clustered index. And the difference between the two is that a clustered index defines the order in which data is physically stored in the table. A non-clustered index defines a separate virtual table, which is an index table, which is going to be sorted while leaving the actual table intact. In other words, non-clustered index are not going to affect the physical arrangement of data in the table. What is going to be done is to create a separate table, which then is going to be sorted, and it's going to have pointers to the data in that table, and there will be values which are going to be stored in that table. Okay. Okay, so when you are looking at clustered indexes, like I said, the data in a clustered index is going to be sorted in order. So if you have a table and you define a clustered index made for student number, the student numbers are going to be sorted in ascending order, and the corresponding values are also going to be sorted accordingly, so that the student who has the smallest student number will be on top, and the student with the largest student number will be at the bottom. Clustered indexes define the physical storage of data in the table. Now, because of this requirement, you can only have 1 clustered index per table. And this is the point where I want to go back to the database. And I've just created this database. I want to insert some values just to illustrate what I'm talking about here. we have a student, maybe a student with number 210, and the first name is Ben, and last name could be Miller. So I have that one student. If you go to my table in the database, I'm using AdventureWorks. This is my table. I have a primary key there. And if you check, that's the name of the primary key. And if you go to indexes, you see the name of the index which has been created. So take note, when you create a primary key for a table, an index is automatically created, a clustered index is automatically created, meaning that the values in that table are going to be stored in order of that primary key field. So if I was to enter another student's record, say 202, something like that. These students are going to have their details sorted according to their student ID, students' numbers. If I add another student, say 07, you are going to see that the student records are going to be sorted according to the student IDs. That is because a clustered index has been set on the primary key field. Any questions? Any questions?
No questions, sir.
Okay. Okay. So we
Sorry,
are
sir.
yes, can go ahead.
When you're talking of the table, sir, I can't see the table.
Or you can't see the table.
Yes, I'm just seeing the clustered index and the points. The slide, all I can see is the slide.
You are not able to see, is that the experience of everyone?
Yes. I would like to see an example.
Okay, I need to. I should have switched now.
Yes, now it's showing.
Yes.
Okay.
Showing, sir.
So that's a table I've created with just these fields. And I started by inserting, okay, let me just insert the data again. So I'll delete everything from there. Okay, so suppose the first student has the ID 299 and the first name is Steve. Njovu. So I have one student there. I add another one, maybe 107. Monday. Minga. So you notice that the records are not being sorted, are not displayed in the order in which I've entered them, but rather in the sequence according to their student IDs. That is because when you create a primary key on this table, there is an index which is automatically created, this one. And you can see in brackets, it's indicated this is a clustered index. And we are saying clustered indexes are those where data in the table is going to be physically arranged in that order. So for clustered indexes, they are going to affect the physical arrangement of data in the table. The idea is if we are looking for a student with student number 250, we are not going to check each and every record in this table. We are going to go to the middle of the table and check is this student number greater than the value, the student number we are looking for? If it's not, then we look in the bottom half of the table. If it's less, we look at the top half of the table. Okay, let me add another student, maybe a student with 224. So you can see that it will keep arranging them physically according to their student numbers.
Yeah.
That is a clustered index. Now we're saying only one clustered index can be defined per table. We cannot have maybe two clustered index. We can only have one clustered index for each table. Now, you may be asking, how does this work in actual databases? The steps followed are as follows. First, the SQL Server is going to obtain the address of the root page, which is this one. Are you able to see my paint?
Yes.
No.
You can't see paint. Oh. Okay. Are you able to see it now?
Yes, now
Yes.
it's showing.
Okay.
Able.
So this is a diagrammatic representation of the B tree data structure. We said it looks like an invented tree with the root on top and the branches at the bottom. And to determine this is calculated using some formula, and I've given you this formula. You don't need to memorize this. So if the first record is number 1, and so saying low, 1, high is equal to maybe 20. It means that we're going to say 1 plus, in brackets, 20 minus 1 divided by 2. Sorry, here it's supposed to be divided by 2. Okay. And this answer is what is going to be stored in a system table. Remember, we did talk about system tables in SQL Server. So one of those tables is a table called System Indexes Table. And this is where, for each database, there will be the root page stored for tables where you have defined the clustered indexes. So when searching, when you want to execute a query, you want to look for a student with a student ID number 275. SQL Server will first go to this table and obtain the root page. Which will be this one. Then it's going to check. This number is maybe 240, and I'm looking for student number 275. Because the number that I'm looking for is less than what is here, I'll go to this branch maybe. And when I get there again, it will calculate this value using the formula and then determine whether to check this side or to check this side. Okay. So the first step is to get the root page or root node from the system indexes table, which is a system table. Once that has been obtained, the second step is to check the search value, the value that you are searching for. That is, in this case, you are looking for student number 275. Compare it with the root page value. Is it less or equal to it, or is it greater than? Okay. The page with the highest key value less than or equal to the search value is found. What I mean is this. If the root page is 250 for argument's sake, and we are looking for 275, then that value is less than or equal to the search value. So it's going to take the lower part of the table. So it means that by just one comparison, it has cut off half of the table and restricted the rows where the answer could be found to just half of the table. Okay. The fourth step is the page pointer is followed to the lower level index. If I do this, are you able to see my paint?
No, sir.
No.
No.
Okay.
No, sir.
Are you able to see paint now?
Yes.
Yes.
So,
Okay. So once you have determined the part where the value could be, then you go, there will be a key there and a pointer. So the pointer is followed to that section. Now, for that section, you are going to look at the lowest value. So in this case, it's the 251, because we are looking at the lower half of the table. Okay, that's what I mean by this statement. Then step 3 and 4 are going to be repeated until the database software gets to the value that you're looking for by reaching the bottom, which is the leaf level, and has found the answer. Okay. Otherwise, it means that there's no match in that table. Okay, let me show you something which might be helpful. In this illustration, we are looking for, this is a database for employees, and we have an employee table where there are employee details with employee IDs. And we want to look for employee ID E006. Okay. So the first step is the server is going to obtain the root page from the system index table. Next, the server will search for the highest key value of the page, which is less than or equal to the search value. And this will result in the value pointing to where there is E005. This one. Sorry, I made a mistake there. Okay. This is supposed to be E004. Okay. That's the second step. The next is to continue the search from this one, which is page. So everything from E004 going up is found on page 602. If the value was not in this section, the server would have searched in this page. Okay, so it will go to this page, And then again, it's going to perform the same search. And this will lead it to find this one, where there is E005, E006, and so on, which has this page 203. You might ask, where are these page numbers coming from? These are intermediate values which are determined by the server to lead it to the actual tables. So the values there are going to have pointers. These pointers are pointing to parts of the computer memory where the different section of the table are stored. So it's going to look for this section. And again, searching there is now going to find this E006. So you find that by just making 2 comparisons or 3 comparisons, it's able to pick the value from a lot of records in a table. Okay. So it will keep cutting the number of records in a table by half, then takes one of the half. Again, it will divide that by half and it determine which half is the value supposed to be in the lower one or the upper one. Then it will go to that half. Again, it will cut that by half. And so you find that it's able to cut down and get to the answer in fewer steps than checking from the first record, searching all the way up to the end. Now, the point is, if the records are few, the difference will not be significant. But if you have a large table with thousands of records, rows in it, then you are going to see improved performance.
Okay.
Any questions?
No.
No, sir.
I was hoping
Yes,
to, yes, to cover more than one. Yes.
Yes, I wanted to ask something.
Yes.
You said clustered indexes are created at the moment a primary key is set on a table, isn't it?
No.
So
What I said is that clustered indexes are created automatically when you create a primary key. Otherwise, if there is no primary key, you have to create it manually.
okay.
Yes.
All right.
So when you have a primary key, that will automatically be set as is going to be configured with a clustered index. Okay, just look at some more databases we have made. Let's go to this one. There's this department table. It has a department ID as a primary key. So when you check, you see that there is a clustered index created on department ID there.
Yes.
So every time you create a primary key, you are going to have a clustered index created for that column. I need to emphasize this. Indexes can be defined for multiple columns jointly. Are we together?
Okay.
Okay.
So
Yes,
Yes.
sir.
if, for example, you have a table where you have a composite primary key, then the clustered index is going to be defined for all those columns which are part of the composite primary key.
Okay.
Right.
Does that answer your question?
Yes, it's clear, sir.
Okay, okay. So let me go back to okay, this is just the steps that I was explaining. Non-clustered indexes. A non-clustered index contains the index key values and the row locator that points to the storage location of the data in that table. In other words, the physical order of rows in the table is not altered. It's not going to be arranged in the order of the index values. In other words, non-clustered indexes are not going to change the physical arrangement of data in the table.
Okay.
What is done is a separate virtual table is created, which is going to have row pointers indicating row in which the values are and the indexes.
Okay.
Okay.
This is normally illustrated in this way. Think of a non-clustered index as the index found at the back of a textbook. The words which appear in the index are not going to change the page numbers. The page numbers are not going to be arranged according to the index, no, but there is a separate section which is created as an index, and there you have things which are organized in an orderly way. And they're going to have information to point you to the actual and sorted location of what you are looking for. So like I have a book with me. Let me just see the first word which is there. The first word I have is alias. And it's giving me the page number where I'll find the word alias, or the page numbers where I'll find the word alias. Okay. So the physical order of rows is not the same as the index order for non-clustered indexes. This is the opposite of clustered indexes.
Okay.
And a non-clustered index is typically created on columns used in joins, as well as where you have the where clause. Remember from what we have covered in the previous chapters, the joins are used when you are retrieving or querying data from multiple tables. So
Yes.
you're going to have an inner join between maybe two tables. So you can have a non-clustered index defined on that column where you have set the join. Or alternatively, you can have the A non-clustered index defines where you have set the condition. You have a table for employees and you have set a non-clustered index on the maybe date of birth. You can you can define the non-clustered index on date of birth. It's a typical application or area where you can use the non-clustered index effectively. The non-clustered indexes are also created on columns where values are frequently changing. So if you have a table where there are students' outstanding balances, that might be a good candidate for unclustered index. It's the opposite of clustered index. Clustered index, you normally define them where the values are more or less static. They don't change frequently. And the last point is, when you issue the create index command, unless you specify that you want to create a clustered, unless you specify that you want to create a clustered index, SQL Server is going to create a non-clustered index. That's the default.
Why is that?
Well, since there are just these two common use, one of them has to be used. It's like when we're looking at constraints, I don't know if all of you have gone through that. We say that
Yes.
you have a column where a certain value is common. For example, you have a customers table and most of your customers are from Lusaka. So for that column town, you can set the default town as Lusaka so that if the person using the database doesn't change, it will automatically show Lusaka.
Yes.
Yeah. Also, the designers of SQL Server, they have realized that since for indexes, clustered index will only be one index per table, but then non-clustered indexes can be as many as 999. So it's more likely that in most cases, you'll be creating non-clustered indexes. Please take note of such numbers. I haven't checked in the newer versions of SQL Server. This could have changed, but for version 2012, this is the largest number of non-clustered index per table.
Okay.
You can create up to 999 indexes.
Okay.
Okay, that's mine. The data in the non-clustered index column is going to be in random order, because we have said that the non-clustered index are not going to have any effect on the physical arrangement of the rows in the table. So it's just going to be the way maybe the way you entered it, it's not going to affect the arrangement of rows based on that column, because a separate virtual table is created which is ordered, leaving the original table in its unsorted order. So for this reason, it's advisable to create one clustered index, then you can create non-clustered indexes afterwards, because the non-clustered indexes are not going to affect the way the clustered index has arranged the data in the table. Like we said in the, it's a bit, I don't know how best to draw this table, but what you can see immediately is that there isn't there's a bit of disorder or randomness. That is because the data in there, in the original table, is not going to be sorted in any order, but the intermediate tables are going to be rearranged, and these are the ones which are going to have pointers to the values in the table. So this one will have will be pointing to this, the actual table, the value will be there, but in there it will appear there. It will just follow the pointer. This one will be on top here in the intermediate, but the actual table, in the actual table, the data will be in the maybe last page. Okay. So there is no correlation between the physical order and the index order for non-clustered index.
Okay.
Any questions before I look at how to create indexes?
Yes, sir. I want to ask. So you mean non-clustered index are created like by default if you did not specify the kind of index you are creating?
Yes, yes. That's what I'm saying.
Okay, I understand.
So, sir,
Yes.
this is how it's supposed to look, the display, like a non-clustered index is supposed to look like this, the same, like the way the figure looks.
No, this is just a visual representation.
Okay.
Let me make some, and then you see the actual in the actual table.
Okay.
Okay, so let's go to okay. I got this. I'll make another table. Okay, let me copy information in the employee table. I want to see first what is in this one, employee. So, okay. That has 290 rows. Okay. I can copy this into a new table and I'll call it select. into okay. Okay, let me just see. So I've created a new table with all the data that was in the employee table. This one. So if I okay. The reason I've done that is this one will not have primary key, so there's no clustered index. And if you check on the index, there's nothing there. Okay. So now to create an index, you follow the syntax. Create clustered index, and the name you want to give to the index. Then on employee 2. That's the name of the table. And then the column on which we are going to create the clustered index, you put it in brackets. You might also want to specify, say, width. Okay, let me first create it like that. Since I have multiple tables with the same name, I need to be a bit more specific. So you've seen that the schema is DBO dot, and I'll just update this. So I want to create a clustered index on this table, employee 2, and I'm going to use this column in that table. This is the name I'm going to give to the clustered index. So now, if I go to this one, refresh, and go to indexes, then I'll find the clustered index is there.
Okay.
Now, I need to point out this. Although clustered indexes are typically associated with a primary key field, they do not have the same requirements. What I mean is this. A primary key field or column would not accept duplicate, but you can
Yes.
create a clustered key, a clustered index on a column which has duplicates.
Okay.
That's one important difference.
Okay.
Okay. Now, when you have once you have created one clustered index, if you attempt to create another clustered index, you get an error message. So you can only create one clustered index per table.
Okay.
Now, I mentioned about execution plan. You can get some important statistics about the query. For example, we want to select all the records from this table in and dbo.employee where employee ID, employee ID is equal to I don't know, maybe 131. I'm hoping there's something like that. Okay. When you have done that, you can get more information about that query by using a number of tools here. This one says display estimated execution plan.
Okay.
So when I do that, it's going to show me clustered index, SIG, and the employee and so on. So when I point on it, I see some more details and so on.
Okay.
It's giving me, before I even execute the query, it's telling me, giving me some statistics. I don't know if you're able to see now. It's estimated operator cost, 100%, estimated input output cost, 0 points. So you can compare the effects or the efficiency of different queries. The second one, I'm not going to set the primary key. Are you able to see the differences in terms of figures?
Yes.
Yes.
You see I'm showing relative cost. The query cost relative to the batch is only 27%. This one is 73%. So you can also show the execution plan by using this tool, include the execution plan, so that when you execute, you can see. Now, just a few things I need to wind up. You've seen this one on top. It's saying, okay, let's see the results. Okay, there is one. But when you come here, observe this. It says a clustered index sig. This one at the bottom, it says clustered index scan. What that means is that for a scan, it reads all records in the table from the beginning up to the bottom. That's why it has this high cost.
Okay.
Okay.
But this one is using the B-tree data structure to cut down on how quickly it can get to the record that we are looking for.
Record.
And that's why it has that information. If you point on it, you can also try to compare the values that you get, and you can just have a look at them in your spare time and see the differences. Okay, that's the including the execution plan. This one is includes live execution statistics. When I have this one, I would want to now statistics, more information about the plan is there, and this is the, here it's giving me some details about how this has been executed, as well as this same information, you'll see it also there, okay? Objects and so on. Now, if you have a join, for example, you notice that it might execute the two queries, one query for one table, another query for the other table, then it will put the results together. But when you look at the results, you just see the results that you asked for, but in actual fact, it would have performed two queries. So the execution plan will help you to see visually how the query was executed. And in the live statistics, you have the execution plan as well as the details or the statistics about the execution of that query. Okay, I need to stop here. Any questions?
Not
Yes,
really.
yes. I'll just emphasize this. There's a syntax for creating clustered indexes or non-clustered. If it's non-clustered, we just change that to non-clustered.
Okay.
And what does CIX stand for?
Come again?
The CIX on the syntax there.
I'm just trying, I'm just using that to present non-clustered index, clustered index. So if I want to put a non-clustered, probably I'll start with NIIX to just help me remember that this is a non-clustered index. So for example, is there maybe date of birth? Date birth, okay, let me use that. Date birth. I also want to add maybe that there. Want to create a non-clustered index. on this, it's birth date, sorry. Birth date. I swapped them, and even there, I need to. This will have no effect, just that I'd rather be consistent. Okay. So I want to create a non-clustered index on birth date.
Okay.
So if we go back to this and refresh, so we now have two indexes. There's this one in brackets showing clustered, then there's this other one which says non-unique, non-clustered on the bed. Okay. So that's the syntax for creating indexes.
Okay.
Any questions?
No.
No question.
Okay, sorry about the sound. I think I had plugged in my headset and it wasn't fully inserted. So
Okay.
I'll come and look at managing indexes, how you can disable index, how you can enable an index, how you can rename an index or delete, that is drop index. If you have time, please go through that.
Okay.
And
Okay.
yeah, it's not much. It's just a syntax, which I should be able to give you in the course of next week. Yeah, then we can look at views after that. Okay, I need to stop here for now, unless there are pressing questions.
No.
Okay.
Nothing, sir.
Thank you, sir.
No one,
Thank you.
some people have not said anything. I'm wondering whether they have been following.